Look at this building. Before anyone moved in, switched on the lights, or turned on the heating, thousands of tons of carbon dioxide may already have been released. Much of it comes from one material: cement. Now consider the buildings, roads, bridges, tunnels, dams, and ports being constructed around the world. Cement is essential, but it has a carbon problem. Its production accounts for around 7% of global carbon dioxide emissions. And the most difficult part is not just the fuel used to make it, it is also the chemistry. Even if every cement plant switched entirely to clean energy, a large share of those emissions would still remain. So where does all that carbon come from? And what would actually have to change to reduce it? In this series, we break down the products, processes, and technologies behind modern industry. We explain how they work, why they matter, and the engineering challenges shaping their future. Welcome to Explained! Part of cement's carbon footprint comes from the enormous amount of heat required during production. Inside a cement kiln, the material reaches temperatures of around 1450 degrees Celsius. Traditionally, reaching those temperatures depends on fuels such as coal, petroleum coke, or natural gas. Fuel and energy use create roughly 40% of cement's emissions. That sounds like the obvious problem. Replace the fossil fuels and the emissions disappear. Except they do not. The larger source is hidden inside limestone, the main raw material used to produce clinker, which is formed by heating the raw materials in a kiln before being ground and blended into cement. Limestone contains carbon locked inside calcium carbonate. When it is heated, that compound breaks apart and releases carbon dioxide. This reaction is called calcination, and it creates roughly 60% of cement's emissions. It is not caused by an inefficient machine. It is built into the chemistry of conventional cement production. That means clean energy alone cannot solve the problem. The materials themselves also have to be reconsidered. But the world cannot simply stop using cement. It remains essential for housing, infrastructure, transport, energy systems, and urban development. So the real challenge is not choosing between building and reducing emissions. It is finding a way to do both. Part of the answer may come from using concrete more efficiently. Emissions may also be reduced by changing fuels, improving plant performance, lowering the amount of clinker in cement, and developing alternative materials. For carbon dioxide that cannot be avoided, carbon capture and storage may also be necessary. But there is no single solution. Reducing cement emissions is not one simple upgrade. It requires changes across the entire system. From the materials we select, to the energy plant's use, to the way unavoidable carbon is managed. Cement will continue to shape the world around us. The next challenge is making sure it does so with a much smaller carbon footprint. Not by changing a single step, but by rethinking the entire chain. But the story doesn't end here. In Part 2, we'll look at how cement production is evolving, making cement more sustainable every day. And the solutions may be closer than you think.